For over a century, mathematicians have struggled to solve the Navier-Stokes equations, the rules governing fluid motion. The difficulty stems from an assumption held by early physicists like George Stokes that space is an empty linear void where fluid velocity can theoretically increase without any physical limit. Resolving this problem requires shifting focus away from abstract algebraic manipulation and looking instead at the physical geometry of reality. In a rotating system, the speed cannot increase forever. Once the manifold reaches its pi limit, it hits an absolute rotational velocity ceiling that maintains equilibrium. This pi boundary serves as a geometric governor. It ensures that any energy moving through the system stays within a measurable, finite range. Reality functions as a self-measuring system. The geometry itself provides a physical ceiling that prevents chaotic expansion from becoming infinite. Positioning our view directly above the spinning axis of this system reveals the energetic pole at the center of the manifold. Radiating from this pole is a Fibonacci spiral. It expands outward in a circular pattern, defining the distribution of energy through space. As this spiral elongates, it defines exactly 5 distinct layers of density. These layers form the structure of the inverse quantum sphere. These 5 layers allow the universe to measure its own expansion. Without this internal geometric limit, the system would lack the stability required to exist as a quantifiable reality. This 5-layered structure is the geometric reality that allows the Navier-Stokes equations to remain smooth and regular at any scale. Classical Navier-Stokes math predicts a blow-up scenario, where a shrinking fluid vortex theoretically spins up to infinite velocity. This is the moment where standard equations fail. In a manifold governed by the inverse quantum sphere, that infinite acceleration is physically impossible. The fluid vortex eventually hits the pi rotational velocity limit. When the fluid vortex reaches this limit, it strikes the elastic density of the singularity, triggering torque inversion. Because the fluid cannot spin faster than pi, the kinetic energy is redirected upward into the next layer of the Fibonacci spiral. The energy moves through the 5 layers, being absorbed and stabilized. This handoff prevents energy accumulating, keeping the fluid flow smooth. This torsion clutch mechanism neutralizes chaos. It transforms potentially destructive kinetic energy into geometric stability. This geometric stability is visible in the physical world, specifically in the operation of a high-temperature plasma burner in Gulfport, Mississippi. The burner produces a blue plasma column where a graphite rod is suspended at 4,000 degrees. The flame never touches the chamber walls. The energy is contained within a stable torsional soliton. The 5 layers of the inverse quantum sphere act as a buffer, preventing the thermal energy from bleeding out and melting the container. The burner demonstrates how these geometric principles apply to real-world thermodynamics. It shows that extreme energy can be held in a stable, no-touch state through geometric containment rather than mechanical force. Grounding the Navier-Stokes equations in this specific geometry reveals a 5-layer structure that also appears in other areas of physics. The inverse quantum sphere suggests that other Millennium problems share these same geometric constraints. If space is self-bounding, the math governing particle mass and manifold topology could follow the same rules. Problems like the Yang-Mills mass gap and the Hodge conjecture become clearer when the underlying space is viewed as a self-bounding torsion spiral. This approach provides a consistent framework that sidesteps the high-energy chaos seen in purely reductionist models. By observing how geometry behaves at its limits, the resolution to these problems is found through the perception of physical boundaries. The focus shifts from merely measuring the chaos of a storm to calculating the exact geometry required to stabilize its core.